Okay, so on Tuesday, we were talking about units. One of the units that we'll be talking about is volume. Now, when we think about volume from a geometry standpoint, we think about the volume of shapes. And the volume of shapes have their own equation. For instance, the volume of a sphere is 4/3 pi r cubed. The volume of a cylinder is pi r squared times the height. The volume of a square is length times width times height. Will we ever use this? Yes. Do we use it frequently? No. The reason is because shapes mean that you have something that is regularly shaped. These equations mean you have a regularly shaped object. Now, with respect to volume, when we're talking about these regularly shaped objects, we're typically talking in cubic meters if we're talking about the SI unit, or cubic centimeters. However, in chemistry, many of our substances are irregularly shaped. If they're irregularly shaped, we can still talk in terms of centimeters cubed, but we're going to have to figure it out a different way, which we'll talk about when we get into density. But also, many of our substances are liquids, and therefore we tend to use the term liter or fluid ounces. And yes, if we're talking about in the English system, the American system, we talk in terms of gallons and quarts. Now, some volume conversions. 1 milliliter equals 1 centimeter cubed. That is the one that I told you you have to have memorized. The reason you have to have that one memorized is because it is something that is used frequently, especially in the pharmaceutical and medical world. When we're talking about suspensions, a lot of times we are told to take a cc or 2 cc's or something of that nature. But the device that they give us at the pharmacy is in milliliter. So it's important to know that it's a 1-to-1 ratio. Another one that you should know that you need to have memorized is that a liter is 1,000 milliliters. That is the metric prefix conversion factor. The rest of the ones up there, you will be given. I'm not expecting you to know the English to English system. I'm not expecting you to know the English to metric system. But I do expect you to know those two. In fact, and I did not get it printed off yet, so you will receive it on Tuesday. You're going to receive this table with your exam or exams, which has a lot of the conversion factors in it. It even has a couple here and there related to SI to SI or metric to metric, but you can't guarantee that. As I said at the end of class on Tuesday, you have to know the metric prefix conversion factors. I'm not giving those to you. I mean, it may be in the table, but you can't guarantee it. And you need to know 1 centimeter cubed or 1 cc is equal to a milliliter. Those are the ones I'm having you memorize. But otherwise, you're going to get a table. With their equivalents. Any questions about units? Again, a measurement is invalid if there is not a unit associated with it. Masses, I better see something like grams or kilograms or something of that nature associated with it. Lengths, I better see meters or centimeters or something associated with it. Time, I better see seconds, minutes, or hours. Because again, a unit is invalid. A value is invalid if there is not a unit associated with it. Now, a very important set of units that we work with is density. The density, okay, folks, if I go weigh you, does that tell me anything about you except your mass? No. Could there be somebody else with that same mass? Yes. Mass by itself does not identify an object. The amount of space you take up, your volume. Somebody else in the world could have the exact same volume. The volume by itself does not tell me who you are. But density is a value that when combined with other values can really help us identify an object. You will be working with density in the lab. Obviously, there's not one Monday, so the week after, on the 8th, I think it is. But density is something that can be determined, and we can use it to help identify an object. What is density? Density is mass divided by volume. It is a derived unit where density equals the mass divided by the volume. Mass and volume by itself are extensive properties. Again, it's a property that depends. What an extensive property is, it's a property that depends upon the quantity. But when you put mass divided by volume and you get density, density is an intensive property. An intensive property is one that the reason it's so useful is because it is independent of the quantity. What that means is no matter where I go dig up some copper, no matter where I find that copper wire, as long as it's copper, it's going to have the same density. No matter if I have a piece that's this long or a piece that's this long, it's going to have the same density. Because it's an intensive property. Now, what do we mean by density? When you look at these two objects, let's assume that each ball represents a mass. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I hope you can see number 13 very well. in this volume. Over here, I have many more in that same volume. This one has a lower density because it has less molecules per space than this example. Again, it's mass divided by the volume. Here are some densities of various substances. The air you breathe is a mixture of gases that has a density around 0.00129 grams per centimeter cubed, or grams per milliliter. A centimeter cubed is an extremely small object. Whereas, if you look at glass, which we know is a solid, it has a density that is much greater. It has a density of 2.6 grams per centimeter cubed, meaning there's a lot more molecules within that centimeter cubed. It's a lot more dense of an object. Now, one thing I want you to note up here is we have ice, which is solid water. It has a density of 0.897. But liquid water at 4 degrees Celsius has a density of 1.000. What I am trying to illustrate with that is density is temperature dependent. Density is temperature dependent. Now, admittedly, most objects in solid form have a higher density than do their liquids. And most liquids have a higher density than do their gases. Ice is an oddball. Ice is an oddball with respect to its solid density, and it's simply the reason ice is an oddball is because ice is actually mostly air. But taking that away, the main thing I want you to note is density is temperature dependent. We can see that when we look at the states of matter. You have a solid. Most solids, the molecules are arranged in a very ordered array. The individual molecules are extremely close to one another. And therefore, they have a high density because you have a lot of molecules in a given amount of space. Now, when we heat up a solid to make it into a liquid, what we're doing is we're breaking some intermolecular forces, which you'll talk about in College Chem 2. We're breaking up some intermolecular forces, and the individual molecules, they spread out some. Now, because there is more space between those molecules, a liquid tends to be less dense than does a solid. Again, water is an oddball. But most substances, the liquid is less dense than a solid, simply because there's more space in between the individual molecules. Now, when you get to a gas, you have broken all intermolecular forces. And when you break all intermolecular forces, these molecules are way apart from each other. There is a lot of air in between the individual molecules. Because there's a lot of air in between the individual molecules, if you're talking about a gas, it's going to be much lower density than its liquid. So water is an oddball. It has its highest density right around 4 degrees Celsius at 1. But ignoring the left-hand side, what you will notice is that in general, as the temperature increases, the density decreases. As the temperature increases, the density decreases. Now, density can also be used to create a density column. When it's raining and it's just started raining, if you go to a gas station, you will typically see a rainbow film on top of the water. That is because gas is less dense than water. Oil is less dense than water. So if you ever make a oil vinaigrette, it separates out with the oil sitting on top of the vinegar, which is mostly water. Oil is less dense than water, so it floats on water. Milk is more dense than water. Because milk is more dense than water, it will sink relative to the water. The reason milk is so dense is because it has a lot of fat molecules in it. And then you have honey, which is what that's supposed to say. Honey is more dense than milk. And so the milk will float on honey. So we can create a density column. Now, these densities of liquids can also be used to identify the approximate density of a substance. Because if I take an object and I put it in water and it floats, it means its density is less than that of water. If I put an object in water and it sinks, it means that that density is more dense. That object is more dense than water. If it sits in the liquid, it means it has the same density as water. Next, no, the 8th. One of the things you will be doing is identifying the type of polymer or plastic that some objects are made out of by their density. And the way we're going to do that is we're going to set up a series of liquids with differing densities. And you're going to put the object in each of those liquids. And you're going to determine, does it float, does it sink, or does it sit in the middle? And by comparing how that object behaves in all of the liquids, you're going to be able to determine the approximate density and therefore the identity of the polymer that plastic was made of. So we can use density again to help us identify a substance. We can either measure the density directly to help us identify the substance, or we can create a density column or a series of solutions of differing densities to determine the approximate density of the object. So let's look at some problems. of density. A nugget that we think is gold has a mass of 22.5 grams and a volume of 2.38 centimeters cubed. Is the nugget pure gold? Pure gold has a density of 19.3 grams per centimeter cubed. What I note is I have mass and I have volume. Mass and volume means I'm going to calculate the density. Density is mass divided by volume. So therefore it is 22.5 grams divided by 2.38 centimeters cubed. And this comes out to be 9.45 grams per centimeter cubed. So therefore, this is not pure gold. Because it does not have a density equivalent to that of gold. Questions? I'm watching people write if you're wonder why I'm pausing. Okay. Let's look at another one. What is the density of a lead block with dimensions of 4 centimeters by 3 centimeters by 6 centimeters if the block has a mass of 820.8 grams? Because this is a regular shape, we can use the equation that volume is equal to the length times the width times the height, which is the equation for volume when we're dealing with a cube or a rectangle. So therefore, our volume is going to be equal to 4 centimeters times 3 centimeters times 6 centimeters, or in other words, 72 centimeters cubed. Now that I know the volume, I can determine the density because density is mass divided by volume. Therefore, it's going to be 820.8 grams divided by 72 centimeters cubed. And we get a value of 11.4 grams per centimeter cubed. You don't have to memorize the formulas for geometric shapes. I will give you the formulas of geometric shapes. If you need them. Questions? You are very good catch. It would be 11 grams per centimeter cubed. Anybody want to tell me why? Actually, it would be 10. grams per centimeter cubed. Which one's correct? The last one. Let's talk why. One significant digit times one significant digit times one significant digit. Means that we should have one significant digit. Then we have four significant digits divided by one significant digit. So therefore, we should have one significant digit. So it would be listed as 10 grams per centimeter cubed. There's the reason that works is because that's an implied decimal place. And if you'll remember, trailing zeros with an implied decimal point are not significant. Now, I will say I'm going to make your life a little easier. There will be 3 questions on exam 1 and on the final exam that I specify. You must give me significant digits. Otherwise, it's all in the lab. Your lab will always have to be to significant digits. But on exams, if you'd have listed 11.4, I would have accepted it. Because on exams, only there's 3 questions that will request significant digits. Otherwise, I let you get away with it because I want you to focus on how to do things more than the significant digits. And on an exam, you only have a certain amount of time. Whereas in lab, you got a lot longer. Yes.
Like if you were doing your own research, would you still do significant digits? Because that would kind of like fudge whatever you would measure.
When I do my own research, I always keep up with significant digits, just like I did here in my notebook. But when it comes to reporting something in literature, then yes, I have to report it as 10. Even though that makes it off because of sig figs. Again, folks, this is a great example. Your instrument makes a difference. If you want to be able to report better, then use a better instrument. The instrument makes a difference. But that is a great catch back there. Somebody was thinking of sig figs. Okay, so regular objects are easy to determine the density because you simply pull out your ruler and you measure them. But what about an irregular object, such as this water bottle? It's not a cylinder. Not a perfect cylinder, at least. So how am I going to determine an irregular object? Well, one of the best ways to determine an irregular object is through the process of displacement. In this particular case, we started out with 600 milliliters of water. And we took a rock that weighed 482.63 grams. We placed that rock in the water. And because no 2 objects can occupy the same space, it displaced 200 milliliters of water. That displaced volume, that difference in volume, is equal to the volume of the object. Again, this works because no 2 objects can occupy the same space. Therefore, if I were to determine the density of this object, it would be the mass at 482.63 grams divided by 200 milliliters. Therefore, the density would come out to be 2.4 grams per milliliter. Now, why did I record it as 2.4? It's sig figs. Technically, according to this device, you know the hundredths place. So what is your estimated digit? The tens place. So therefore, if that's the case, then those two digits were significant. So I took 5 significant digits divided by 2 significant digits to get 2 significant digits. The implied decimal rule is not associated with this 200 because it's a measurement. It wasn't a number I just gave you. It was a measurement that we took. Okay, I know you can't read this one, so I'll read it out loud. Why would we want to do some of this? Well, this man received a ring from his fiance who tells him that it is made out of platinum. Before the wedding, he notices that the ring feels a little light for its size and decides to measure its density. He places the ring on a balance and finds that it has a mass of 3.15 grams. He then finds that the ring displaces 0.233 milliliters of water. Since that is the amount it displaced, that is the volume. Is the ring made of platinum? At 20 degrees Celsius, platinum has a density of 21.4 grams per centimeter cubed. So we take our density and we do mass divided by volume, which is going to be 3.15 grams divided by 0.233 milliliters. And therefore, the answer is 13.5 grams per milliliter. Now, platinum has a density equal to 21.4 grams per centimeter cubed. Here's another example where if you know centimeter cubed is equal to a milliliter, then you know it's all this number 13.5 is also the value if it's grams per centimeter cubed. So no, it is not platinum. Yes. The significance of 20 degrees Celsius is, again, density is temperature dependent. So the density would be different if it's at a different temperature.
So it's, okay, I just the word therefore that I was trying to understand. It was platinum density.
Yes, it's platinum density at 20 degrees Celsius. Other questions? You now should have all you need to do the homework. Okay. I'm gonna skip energy. I thought I would go over energy, but I'm gonna skip energy and I'm going to move on to dimensional analysis. We will come back to energy at the end of the semester, so you're gonna see it. It's just when you're gonna see it. That's the difference at this point. Dimensional analysis. Dimensions. Units. In other words, we perform calculations by paying attention to the units. Dimensional analysis is the process of using units as a guide to solving problems. We pay attention to the units. That's what it means. What we use in dimensional analysis are called conversion factors. Conversion factors are fractional quantities with units that are used for converting from one unit into a new unit. You can use equalities such as 12 eggs is in a dozen as your conversion factor. So if I ask how many eggs are in 3 dozen, what would you answer? 36. You just used a conversion factor. Now it's one you're very confident with. It's something you've used a lot. If I said, how many inches are in 2 feet? You would say 24, because you know there's 12 inches to a foot. It's a common conversion factor. All we're doing when we do conversions is we are using these equalities and turning them into fractional quantities that allow us to convert from one unit into a new unit. Conversion factors are constructed from any two quantities that are equivalent. 1,000 milliliters in a liter, or 1,000 milliliters is equal to a liter. That's an equality that we can use as a conversion factor. 2.54 centimeters is equal to 1 inch. That is an equality we can use as a conversion factor. Now, I will say, I do want to say one other thing. While conversion factors are commonly constructed from any two equivalent quantities, when we get into stoichiometry, which is simply mathematics associated with chemistry, we will also use ratios as our conversion factors. Now, there are problem-solving strategies. And I use this strategy. I may not say every step every single time, but I'm using this strategy within my process. The very first part of the strategy is identifying the starting point. This is going to be within the information that is given in the problem. Now, I would say about 90 to 95% of the time, it's going to be a quantity that has a single unit associated with it. Step number 2 is to identify the endpoint. What is it that we want to find? Folks, step 1 and step 2 they're not so bad. It's step 3 that's the challenge. Because step 3 is to find equalities or conversion factors that are going to allow us to make that conversion. Now, as we go through this, I am going to try and help you figure out, where do I go? What do I look for? How can I figure out what conversion factors I need? What equalities do I need? That's one of the things I will discuss. Then we solve the problem using dimensional analysis, meaning we pay attention to the units. The units are used to perform the conversion. Now, a lot of folks skip this last step. The last step is to see if the answer makes sense. And also to check this number of significant digits. Now, I will give you a little hint with respect to those significant figures. Go back to the problem. Look at the numbers in the problem. Your significant figures are almost always determined by the numbers in the problem, not by the equalities that you pull up. Questions so far? I already did this one. Convert 36 eggs into a dozen? Okay. Although we've done this, although you can do this in your head, let's use the steps. Number 1, we're identifying what was given in the problem. We were given 36 eggs. Number 2, identify what it is you want to solve for. We want to know how many dozen that is. Number 3, identify possible equalities. Well, we know that there are 12 eggs in 1 dozen. Step 4, perform dimensional analysis. You're going to start with the value that you have from the problem. And then you're going to use the equality. Now, folks, I use this railroad track method. Many people use this railroad track method because what you will notice is if eggs is in the numerator in this piece, then when we get to the conversion factor, eggs has to be in the denominator because they have to cancel. So what you did in your head is you divided by 12 eggs to get to the dozen. And you divided by 12 eggs because you knew the eggs needed to cancel out. And therefore it was 3.0 dozen or 3 dozen. Technically, it's 3.000000000. Keep going. Dozen. Why? Because 12 eggs, you can't have a partial egg. A dozen, you can't have, I mean, you can have a partial dozen, but they're counting numbers. Counting numbers are exact numbers. So technically you can just record this as 3 dozen. It doesn't matter on this one whether you use 2 sig figs or not, because it's infinite numbers of sig figs. Let's look at another one. Convert 12.5 inches into centimeters. You start by listing what you have. You identify what you want to solve for. You then figure out possible conversion factors. And if you look up a table, you're going to find that 2.54 centimeters is equal to 1 inch. And this is an exact equality. They typically write the word exact by it to let you know that these actually have infinite number of significant digits. So now to do the conversion, we take the 12.5 inches and we need to convert that into centimeters. The inch is placed in the denominator so that the unit will cancel out. The centimeters are placed in the numerator. And you get the value of 31.75 centimeters. Now, with respect to significant digits, your first value has 3 significant digits. 2.54 centimeters in 1 inch, I said, has an infinite number of significant digits. This is multiplication and division, and according to the rules of multiplication and division, the answer will have the same number of significant digits as the measurement with the fewest. The measurement with the fewest had 3 significant digits. Therefore, your answer needs to only have 3 significant digits. So you would record it as 31.8 centimeters. Questions? Convert 120 milliliters into a liter. You start out with what you were given, which is 120 milliliters. You identify what you want to solve for. I want liters. The next thing I do is figure out a conversion factor. Now, here's the first thing I want to help you with. The term milliliters and liters, they have something in common. They have the word liters in common. Since they have the word liters in common, that means you're going to use your metric prefix conversion factor. If these two didn't have anything in common, go find a table. But as long as they have something in common, that means you're going to be using your metric prefix conversion factors. So, my metric prefix conversion factors, I have 2 choices. I can use 1,000 liters is equal to 1 liter is equal to 1,000 milliliters. Or I can use 10 to the minus 3 liters is equal to 1 milliliter. Now we solve. So 120 milliliters. The milliliters have to cancel. So I'm going to place the 1 milliliter in the denominator with the 10 to the minus 3 liters in the numerator. The milliliters canceled, leaving liters. When you key this into the calculator, you'll get a value of 0.12 liters. That's what it's going to look like in the calculator. The question is, how many sig figs should I use? My first value has how many significant digits? I heard 2 and I heard 3. It's 2 because there is an assumed decimal point. Because there is an assumed decimal point, that means that 0 is not significant. So there is only 2 significant digits. Your metric prefix conversion factors are exact quantities. Therefore, they have an unlimited number of significant digits. This is multiplication and division, and according to the rules for multiplication and division, the answer will have the same number of significant digits as the measurement with the fewest. Since the measurement with the fewest had 2 significant digits, your answer will have 2 significant digits, and therefore you would record it as simply 0.12 liter. Questions? Oh, it's going to get tougher. I started out simple. And I'm going to pick up with more complicated on Tuesday.